All right, let's dive right in. We're about to start a journey into the very heart of matter itself. We're going to be exploring the incredible, almost unbelievably powerful world that's hidden deep inside the atomic nucleus. So, yeah, let's get started.
So everything really kicks off with this one enormous question. What actually holds the universe together? Seriously, think about it. Everything from the stars burning millions of light years away to the very chair you're sitting in right now. It all boils down to just a handful of fundamental particles and the forces that govern them. And to really get a grip on that, we have to shrink ourselves down to the smallest possible scales.
Okay, so here's the plan. First, we'll look at the atom's hidden core. Then we'll talk about the two main families of particles, matter versus force. After that, we'll get into the four fundamental forces, touch on some really cool kind of spooky rules about symmetry, and finally, we'll learn about the special measuring stick physicists use for all this stuff.
All right, section 1. Let's start with something we all kind of know, right? The atom. You've seen the picture, a bunch of electrons buzzing around some central point. Well, for what we're doing today, we're actually going to pretty much ignore those electrons. Our entire focus is on that tiny point in the middle. We are zooming way in.
And get this, just let this sink in for a second. Over 99%, so basically all, of an atom's mass is packed into that ridiculously tiny spot right at the center. It's just an insane concentration of matter and energy. It's almost impossible to wrap your head around.
And that spot, as you probably guessed, is the nucleus. It's made of just two types of particles. You've got your positively charged protons. The number of protons, which we call Z, is what makes an element what it is. And then you have neutrons, which, as the name suggests, have no charge at all. It was really the discovery of the neutron by James Chadwick that blew the doors open on our modern understanding of the nucleus.
Okay, now we're getting to a really central idea in all of physics. It turns out that every single particle in the entire universe, everything we have ever found, can be neatly sorted into one of two fundamental families. It's like the universe has two completely different types of building blocks.
So first up, you've got the fermions. These are the building blocks of matter. They're the literal stuff that things are made of. Your electrons, protons, and neutrons, they're all fermions. And they have this one absolutely defining rule called the Pauli exclusion principle. What it basically means is that fermions are total individualists. No two identical fermions can ever be in the exact same quantum state at the same time. They demand their own personal space.
And the other family? Those are the bosons. So if fermions are the bricks, then bosons are the mortar that holds them together. These are the force carriers. They're like little messengers running back and forth telling the fermions how to behave and interact with each other. And they are the complete opposite of fermions. They're total collectivists. You can cram as many bosons as you want into the very same state. That's actually how you get things like a super-focused laser beam.
So let's just quickly break this down. You can see the big differences right here. Fermions, they build the matter. Bosons, they carry the forces. Fermions follow that Pauli exclusion principle. They need their space. Bosons, they can all pile into the same state, no problem. And then there's this weird quantum property called spin. You can sort of think of it like a tiny, built-in rotation. Well, fermions have these half-integer spins, like 1/2 or 3/2, while bosons have integer spins, like 0, 1, or 2. The classic example of a fermion is the electron, and for a boson, the photon, which is the particle of light. Okay, let's talk about the forces themselves. How does all this stuff actually interact? Well, what's amazing is that every single interaction in the entire cosmos, from a galaxy spinning in deep space all the way down to a single particle decaying inside a detector, it's all governed by just four fundamental forces. That's it. Only four.
So number one, and for what we're talking about, the absolute king, is the strong force. This is like the universe's superglue. Its job is to bind protons and neutrons together in the nucleus. And you really have to think about what that means. You've got all these protons, all positively charged, all hating each other and trying to fly apart with incredible electromagnetic force. The strong force has to step in and overpower that repulsion. And man, does it ever. It's way, way stronger. Then, number two, you have the electromagnetic force. This is the one carried by photons. It's responsible for all of chemistry and light. But inside the nucleus, its main role is that repulsion I just mentioned. It's trying to tear the nucleus apart. Number three is the weak force. This one's a bit more subtle. It's the force behind certain types of radioactive decay, and it has this neat trick where you can actually change one particle into another. And finally, number four, good old gravity. Obviously, it runs the show on the scale of planets and stars, but down here at the nuclear level, it is so unbelievably weak that we can basically just ignore it completely.
All right, let's shift gears a little bit. We're about to touch on one of the most profound and frankly beautiful ideas in all of physics. See, it turns out that some of the most fundamental rules of our universe, the laws we thought were just laws, aren't arbitrary at all. They're actually the direct result of deep, hidden symmetries in the very fabric of reality.
And here's the core idea. It's a statement that is both simple and unbelievably powerful. It says that for every single continuous symmetry you find in the laws of nature, there is a matching quantity that must be conserved. And when we say conserved, we mean it can't just be created out of thin air or destroyed into nothing. The total amount of it has to stay the same.
So what does that actually mean? Well, check this out. The laws of physics work the same here as they do on the other side of the galaxy, right? The fact that space is uniform like that symmetry is the reason momentum is conserved. Or how about this? The laws of physics don't care if you're facing north or east. The fact that there's no special direction in the universe, that symmetry gives us the conservation of angular momentum. I mean, that is just a stunningly elegant connection, right?
Okay, but what about a different kind of symmetry? Not about moving or turning, but about reflection. This brings us to a concept called parity. And the question it asks is actually pretty simple. If you were to watch some physics experiment happen in a mirror, would the reflection you see also be a physically possible event? Does the mirror world obey the same rules as our world?
Now, in the quantum world, we describe particles with something called a wave function. And if a particle's wave function looks exactly the same in the mirror, we say it has even parity. If its mirror image is perfectly flipped, like the exact inverse, we say it has odd parity. And for a really long time, everyone in physics just sort of assumed that the universe as a whole had to be perfectly mirror symmetric. It just made sense, right?
But then, something happened. One of the single most shocking discoveries of the 20th century. Physicists found that, the strong force and the electromagnetic force, they both conserve parity. They look perfectly normal in the mirror. But the weak force, it doesn't. The weak force violates parity. It's like finding a crack in the mirror of the universe. It means that on a fundamental level, the universe can tell the difference between left and right. This was an absolutely huge deal.
Okay, for our last section, let's get a little more practical. I mean, the scales we're talking about here inside the nucleus are just so mind-bogglingly small that using our everyday units like meters and kilograms gets really annoying and cumbersome. The numbers are just awful. So nuclear physicists came up with their own special set of units.
So when it comes to length, we don't talk in meters. We use the femtometer, which has the cool nickname of a Fermi. A femtometer is 10 to the minus 15 meters. That's a decimal point, 14 zeros, and then a 1. It is absurdly small.
Now for area, things get even weirder. We use a unit called the barn. Yeah, like on a farm. A barn is 10 to the negative 28 square meters. And the name actually comes from a physicist's joke. Back in the day, when they were trying to measure the chances of one particle hitting a nucleus, they said the nucleus looked so big, it was like trying to hit the broadside of a barn. And the name just stuck.
And finally, mass. This is where we bring in Einstein's most famous equation, E equals mc squared. Since mass and energy are really two sides of the same coin, it's way easier to just talk about a particle's mass in terms of its energy. The unit we use is the mega-electron volt, or MeV. So instead of some tiny number in kilograms, we just say a proton has a mass of about 938 MeV over c squared. Trust me, it makes all the calculations for nuclear reactions way, way easier.
Okay, let's do a quick recap. This is your nuclear physics starter kit. The nucleus is made of protons and neutrons. All particles are either fermions, which build stuff, or bosons, which carry forces. The universe has 4 fundamental forces, and in the nucleus, the strong force is boss. Symmetries in nature are directly linked to conservation laws. And, super important, the weak force breaks parity. It breaks that mirror symmetry.
So, we've basically set the stage. We've met the main characters, and we've learned the basic rules of the game. But that just leads to the next big question, doesn't it? If these are the rules, how do particles actually decay and transform from one type into another? How does the weak interaction pull off its strange parity-violating magic? Well, that's exactly where we're going next.